Welcome to Global Flood Crosscutting Initiative monthly meeting. Each month we have a distinguished member of our community as a keynote speaker who present their research related to flooding. But before we start with our keynote speaker, I want to give a brief update about the global flood cross-cutting proposal. So we submitted the global cross-cutting proposal to GEWEX hydroclimate panel, a global hydroclimate panel, or GHP, and it is still under review. We haven't heard back from them. So we are hoping to get some feedback from the panel and then revise the proposal and submit it for the final review. Also, we are planning to work on a report for GHP, and we are collecting actually different kind of flood study. So if you have done any research in different aspects of flooding, coming from hydroclimate to flood modeling and flood risk and adaptation, then I would encourage you to put your citation in this Google Doc. I have two brilliant early career scholar helping us with the literature review. So we would be happy to have your citation here so that we can have your results integrated into the GHP report, GHP flood cross-cutting report. So today we have Professor Thomas Wahl from the Central University of Florida as our keynote speakers, and we are grateful for his for him accepting our invite, and I'm sure he got a lot of kind of cool stuff to share with you guys. So before further ado, I invite Professor Wahl to present his research work. So, and after that, we have like, a long discussion because our second speaker, Professor Juan, was not able to make it. So feel free to ask questions or participate in the discussion after Professor Wahl's presentation. Thank you. Thomas, you're ready?
Thank you. Thank you. So that means I'm not under too much time pressure. That's good.
Yes.
Yeah, thank you for those who could join. I know the timing is quite unfortunate for European colleagues busy at EGU, but there will be a recording. So if you are watching this later and you have questions, just feel free to reach out to me, and I'm always happy to chat. The title I picked for this presentation is Compound Flood Hazard Analysis Using Hybrid Modeling. And I'll talk a little bit more about what I mean with hybrid modeling in a second. But first, I want to highlight that the work that I'm actually presenting was done by a student in my group, Praveen Madhuvanta, and a postdoc in my group, Sarah Santa Maria. And it is part of a much larger project, the Megalopolitan Coastal Transformation Hub. It's a mouthful. In short, it's MUC. So this MUC project includes 13 different institutions. It's funded by the National Science Foundation under the Coastlines and People program. And the whole project focuses on this megalopolitan area, the US Northeast area, encompassing Philadelphia, New Jersey, and New York. And it's guided by those 4 principles that are written here, which I'm not going to go into details, but I just want to highlight that the work that we do is a small piece of a much bigger puzzle. And I'll come back to that later on my last slide when I outline what we do with some of the results that we have produced in this project to address those 4 guiding principles. Our part of the project, as the title indicates, focuses on compound flood hazard analysis. We use hybrid modeling for that. And again, I'll say in a second what that means. With the audience here, I don't think I have to explain what compound flooding means. I have this little sketch here on the left-hand side, which basically shows that we refer to flooding that can come from different drivers: rainfall, river discharge, storm surges and waves, or the combination of those leading to compounding effects. We also know that observational data of flooding is pretty sparse. Even though flooding happens more and more frequently, we still don't often have a good understanding of how deep it was and how widespread it was. But we do have relatively decent data of the flood drivers that can come from in situ measurements, remote sensing from reanalysis products, model hindcasts, and we can do statistical analysis on the data of these flood drivers. The actual flood hazard, the actual inundation, can be modeled with physics-based approaches. And when I talk about hybrid modeling here, I just mean that we are doing some statistical modeling. In our case, we do multivariate extreme value modeling to then inform physics-based modeling, which gets us to the actual flood hazard. So that combination is what I mean when I say hybrid modeling. And the results I present today are for a case study in Gloucester City in New Jersey. That's a small municipality on the Delaware River, close to Philadelphia. And it's a very simple statement to say that our case study area is Gloucester City. But it actually took us a year, almost a year in the project, to narrow down Gloucester City as one of our first case study locations, because we really wanted to work with communities that are resource staffed, they don't have a lot of capacity, they have important climate risk decisions to make in the near future. They're already impacted by flooding from different water sources, rainfall, coastal flooding, a lot of socially vulnerable people within their district. So there was a lot of stakeholder engagement going on in the first year, a lot of interviews with many stakeholders in this megalopolitan region. And in the end, we narrowed down on a set of different case study locations, and Gloucester City turned out to be one of them. And there's an excellent paper that my colleague Casey Helgeson led that was published in Earth's Future this year about this exploratory scoping of place-based opportunities for convergence research. And that's really what we want to do in this project. Lucky for us, Gloucester City also has pretty good data coverage. We have almost 100 years, or even more than 100 years of rainfall data from the Philadelphia rain gauge here at the airport. We also have 100 years of coastal water level information from a tide gauge here in Philadelphia that measures the water level that is influenced by both the tides and storm surges from the coast, but of course also the river discharge in the Delaware River. And we have the AORC analysis of record for calibration rainfall reanalysis. That one covers about 45 years, has a spatial resolution of 4 kilometers. The latest version actually has 1 kilometer resolution, and temporally it has a resolution of 1 hour. So those are the three main data sets that we use in our analysis to represent the flood drivers that we care about, which is rainfall and high water levels in the Delaware River, which is the coastal component. And the first thing that Praveen did in a paper that was already published last year is develop a joint distribution. So we have those two flood drivers that we worry about, non-tidal residual. We removed the mean sea level and the tide from the observed water levels at the Philly tide gauge. So that non-tidal residual includes storm surge, but also influences of river discharge. And then rainfall here on the y-axis. And we use the 18-hour rainfall accumulation because it has the strongest dependence with the non-tidal residual, meaning that there is a higher likelihood that there is some compounding happening between those two flood drivers. So this joint distribution between 18-hour rainfall, basin average rainfall, and non-tidal residual is based on stratified storm data. So that's something that was very important for us. We took the data and we first identified the tropical storm events, which are the ones shown here in blue. So we have the non-tidal residual values and rainfall values for all those tropical cyclone events, of which we don't have too many, but still quite a few. And the red ones are the non-tropical events, of which we have many more. So we treated those storm types differently because we know they have different characteristics, the marginal distributions of rainfall and storm surge, and also the dependence between those different flood drivers is different for the different storm types. So we analyzed them separately and then brought it back together in the end to derive this joint distribution. Where now on this isoline, for example, every event that falls onto this outer isoline here would be considered to be a 100-year event in this joint probability framework, or a 1% joint annual exceedance probability. And one thing that Praveen then did is he looked at how important are the different storm types in this distribution, depending on the return period that I'm interested in. And you can see the light green here for this 5-year return period event just means that this event or this type of return period in the distribution is dominated by non-tropical storms. And the same happens here for the 10-year and 20-year return period isolines. That just means that if you're interested in things like stormwater management, where we often design for 10, 20-year return period events, you really have to care about the non-tropical cyclones and how they could change in the future if you want to include future projections into your analysis. If you want to design critical infrastructure, flood zoning, and you're interested in 50, 100, or even longer return periods, then it's really the tropical cyclones that you have to worry about because they drive the distribution in this tail. So that was a start. And we also in this paper looked at the effect of convective rainfall events, and we did the same analysis for another location in Florida. So if you're interested, please check this one out. For the purpose here, we want to conduct flood inundation modeling. And for that, this joint distribution, again, is a good start because once we have this joint distribution, we can sample from it. We can generate many, many more of those points, many combinations of non-tidal residual peak and 18-hour rainfall peak, accounting for the dependence strength and dependent structure between those two flood drivers and how it is different for different storms. But at the end, we still only have peaks, and peaks or points in space are not sufficient to run a flood inundation model. So we need to turn those points into time series. And that is what Praveen did in another recent paper that's currently under review, and the preprint is available online, and you can read it there for more details. It's a very busy graph that I'm showing here on the right-hand side, but I'm walking you through it step by step for one event, and hopefully that shows in general the approach that we are using to take those simulations from this multivariate statistical framework and turn it into something that we can use as boundary conditions to force a flood inundation model. So let's start on the top right here. As I mentioned before, from this joint distribution, we can sample many events, and those are the gray dots. The blue ones are the observed ones, combined tropical and non-tropical, and the gray ones are the ones that we just generated with this joint distribution. Now let's assume we pick one of those, and it has a non-tidal residual of 1.75 meters and an 80-hour rainfall accumulation of 80 millimeters. Then next, we pick a rainfall event from the observed event, and we use inverse distance weighting, making sure that it's more likely that we pick one that is relatively close in this 2D space here in this scatter plot. And then we have this rainfall event. From all the rainfall events that are shown here by those gray lines, we end up picking this black one. So that's the one that we selected. And it does not have 80-hour rainfall accumulation, so we need to scale it. So we apply a scaling factor. And we do that for rainfall for all the grid points in our domain, in our model domain that I will show later, and for all the time steps. So that already gives us here at the bottom a spatially varying and temporally varying rainfall field, which we can use as a boundary condition for our flood inundation model. The spatial information comes from this A or C reanalysis data. The same is done for non-tidal residual. We sample a non-tidal residual event, an observed one. All the observed non-tidal residual time series are the gray ones here. We end up selecting for this one the black curves that is highlighted. And again, it needs to be scaled to have this target value or this target peak of 1.75 meters. So we scale it. For the non-tidal residual, we then have to go through a few more steps because we don't want non-tidal residual to be the boundary condition for our flood model. We want still water level, actual water level, to be the boundary condition for our flood model. And that includes mean sea level and tides. And mean sea level and tides vary a lot over the year. There's strong seasonal variability, month-to-month variability, interannual variability, and even decadal variability. So we first want to find out whether this events that we sampled came from the copula, the joint distribution in the previous analysis steps that was derived for the tropical event, or whether it came from the one that was derived for the non-tropical event. In this case here, we find that it was created by the copula, the joint distribution that was fitted to the tropical cyclone event. So we focus on the distribution of tropical cyclone events, the frequency distribution per month of tropical cyclone events, and we sample from that distribution a month. We end up picking the month of July for this event. And then we take all the mean sea level values for the month of July, and you can see there is a spread of about 15 centimeters just within the month of July of the mean sea level values. If you look at the entire year, it's actually several decimeters. So that has a big influence on the flood hazard that we want to calculate later on. Tides also vary over the year, and we want to make sure to not combine a mean sea level value with a tide value or a tide time series that is from winter, and the mean sea level comes from summer, and the storm occurred in February. So we want to be consistent. And again, the gray here are all the tidal segments for the month of July, and we just end up picking randomly this blue one here. So this is our tidal segment that we include to turn our non-tidal residual into a stillwater level. So with that, we have all the ingredients. We can sum them up. We can take the mean sea level value for the month, combine it with the tidal segment that we sampled, and combine it with the non-tidal residual that has been selected and scaled to reach that target value. Now, there's one last step that we need to take, and that is to add a time lag. From a compound flooding perspective, it's quite important how far apart the rainfall peak and the storm surge or coastal water level peak occur. If they're very far away, they are basically decoupled from an impact perspective, and there may not be any compounding happening. If they happen very close to each other, of course, there is a higher likelihood that compound flooding occurs. So we also use the historical data here to sample a realistic time lag for those boundary conditions that we want to use for our flood hazard analysis. And that's just one point. So what I just did and explained was for one specific gray dot here in this upper right panel. We repeat this for all of the gray circles or dots. And in this case, we generated 5,000 of them, which means we turned those 5,000 points into 5,000 synthetic events that are comprised of a spatially and temporally varying rainfall field and a time-varying coastal water level hydrograph. And that is exactly what we want to use as boundary conditions for our inundation model. For the flood hazard modeling, we use SPHINX, super fast inundation of coasts, a model developed by Deltaris specifically for compound flooding. It's a reduced physics model that runs very fast, so it's really well suited for our purposes here. As I mentioned, the flood drivers that we consider are water level. That's our blue boundary here. That's where we force the model with this coastal water level time series that I mentioned. It's kind of interpolated onto this blue boundary. And then rainfall fields over our domain, which is relatively small. It encompasses 2 small watersheds based on the hydrologic unit because there are some creeks that we wanted to make sure are fully captured in this domain. We run the model at 10-meter resolution, but SPHINX has this subgrid routine, which we use to get down to 1-meter resolution while accounting for some of the important local features. And the underlying DM also has a high resolution of 1 meter. Sarah recently submitted a paper to NHAS. It's being processed now. The preprint should be up any day now. If you're interested, check it out or email us and we can share it with you directly, where she explains a lot more about how the model was set up, land use, land cover data that she used, how roughness values were assigned based on that, and so forth. And it also includes a section on validation, which was really tricky. As with many local flood hazard assessments, there was absolutely no quantitative data that we could use, no high water mark, the standard satellite products being way too coarse for our small domain here, SWOT not really being available yet for big events in this area. So we ended up relying on qualitative data. We found some tweets, some pictures of flooding in given intersections that were geolocated. There were some newspaper reports of flooding in certain parts of the city for a given event. We worked with the stakeholders. There were some reports developed by engineering firms that highlighted some of the flood hotspots in the city. So we reran a lot of historic events, or at least a few historic events, where we had some indication of where flooding occurred, how deep it was. And that gave us some trust in the model doing the right thing and producing useful results. The validation, I would say, was successful, but still very limited. And I think that is one of the big issues for the vast majority of local flood hazard studies. If you do large-scale modeling, you will always find a few high water marks within your domain, but still the validation will be quite limited based on this sparse data. So as I mentioned, Sarah then used the 5,000 events and ran them all through that SPHINX model. And now there are different things that we can do with the results of this analysis. And the first thing that we were interested in is to compare what happens if we follow an event-based approach versus what we call a response-based approach in our flood hazard analysis. The event-based approach at the top is basically the one that we use mostly for design, for risk assessment. We define some probability. We say we want to design for a 100-year event. So in this case, we could pick one 100-year event on this isoline because we are focusing on this bivariate framework. Same is done in the univariate world. And we then run this model through this event through a flood model, and we get a flood response. And then we assume that the probability of the flood response is the same as the probability of the event that we put into the flood model. The response-based approach is much more computationally demanding. Instead of just running one event through the flood model, we have to run thousands of events through the flood model. And then we can perform the statistical analysis on the back end, on the actual flood hazard information. So for example, we can calculate the empirical probability distribution for each of those cells in our model domain, and then obtain the 100-year flood depth at each point. And then we assume that the resulting map of that is our 100-year flood hazard map. And we wanted to see how different those are. We wanted to see how even running events with the same probability through this flood model could lead to very different flood hazard outcomes. So in the first step, we picked 25 events on this 100-year isoline. Those are the black dots. So all of those black dots have a joint probability or joint 1% annual exceedance probability in this bivariate statistical framework that we use. And you can see some of them are very close, almost on top of each other. And C and D here on the right-hand side are two examples. The time series here that we see come from this framework that I just showed before that Praveen developed. So we took those points, we obtained those spatially and temporally varying rainfall fields. You can see the hydrographs here, and we created this coastal water level hydrograph. And the one here in the middle and the one at the bottom are C and D here in this inset. Same non-tidal residual, same 18-hour rainfall accumulation. But interestingly, the one in the middle, number C, leads to the largest amount of flooding of all of the events that we obtained from this isoline. And the one at the bottom leads to the least amount of flooding from all the events that we selected from this isoline, despite having the same non-tidal residual peak and the same 18-hour rainfall accumulation. And that is because they get assigned different tide values, they get assigned different mean sea level values, the spatial variability of the rainfall fields is different, the temporal evolution of those non-tidal residuals is different. And that has a huge effect on the resulting flood hazard, even more so than picking different events on this isoline with different combinations of peaks. And that was a quite interesting finding here. On the left-hand side in this figure, we are showing how often a given area in the city is flooded by those 25 events that I showed on the previous slide on this isoline if we run those through the flood model. So if it's green, it means all of those 25 events, any of the combinations of storm surge, rainfall, the different spatial variations and temporal variations lead to flooding in those areas. So those are definitely flood hotspots if we are interested in the 100-year flood hazard zone. The blue areas are only affected by one or two of those 25 events. So if we ended up only picking a few or even just one of those events in an event-based approach, we would probably miss most of those blue areas and not include them in our flood hazard map based on this event-based probability. And the same can be seen on the right-hand side if we look at the standard deviation of the water depth across those 25 events for the different grid cells in our model domain. That leads me to the response-based approach. So the response-based approach, as I mentioned before, computationally more demanding. We now have to run all the 5,000 events through the flood model. And Sarah did that on her personal machine in a couple of days. So again, swings run very quickly. That was a nice thing for us. And then here she created this 100-year flood hazard map or 1% annual exceedance probability flood hazard map using the empirical distribution of the modeled flood depth. So for each grid cell, she has the information of the 5,000 events, which is equivalent to 1,000 years of data. And then through the empirical distribution, she can infer what the 100-year water depths would be in different parts of our model domain. And once we have that, we can then, for example, check what types of events, what types of rainfall and storm surge, mean sea level tide combinations can create this 100-year water depth that we defined based on the response-based approach. So we can trace back the events that cause similar water depths than are shown here in a given area. And what we find is that actually events with much shorter return periods, meaning much higher probabilities, can lead to this 100-year water depth. In the coastal areas, for example, here we have this magenta and blue example, and that's the same color coding that is used here in the plot in the middle, where you can see relatively short return periods, 2 years, 13-year events, but they lead to the 100-year flood depths that we defined based on the response-based approach. And if we look at those non-tidal residual time series, you can see they have prolonged, sustained high water levels, which means they overlap with the high tide, with the higher of the two high tides of the day in this area. And that leads to a coastal water level time series that has relatively high threshold exceedances over multiple tidal cycles. And that leads to this 100-year flood depth for those events, despite the probability of those events being pretty large, because we only account for the peak of the storm surge and the 18-hour rainfall accumulation. We do not account for this temporal variability and the fact that those events are very long, and also not for the fact that they are combined with pretty high tide levels. We also have some pluvial hotspots highlighted here in red and green, and the same color coding is used here on the right-hand side again, where short duration events create a 100-year flood depth. But they have much higher probability in our statistical framework. That is because we use the 18-hour rainfall accumulation in the statistical analysis. So those events that have short pulses over a couple of hours will actually have lower values for the 18-hour accumulation and get assigned relatively short return periods or high probabilities. And we also use the basin average rainfall in our statistical analysis. So we are not accounting for the spatial variability, where in this case here on the top right, we have more rain in the southern part of our catchment, and in the lower one, we have more rain in the western part of our catchment, and that is where the flooding then happens. So we also do not account for this spatial variability of the rainfall in our statistical analysis. So all of that highlights shortcomings when using this event-based approach if we really base our statistical analysis only on a few key variables and not accounting for many other characteristics of the event that really drive the flood hazard in the end. And that gets me to my last slide already. So what else can we do with this data, and what are we doing and will be doing with this data in this larger MAC project that I introduced very briefly at the beginning? We have a really good collaboration going on with Klaus Keller's group at Dartmouth College, where Adam Pollack recently led a paper that was published in PNAS, where we used some of the flood hazard data to assess different funding rules that promote both equity, but also achieve net benefits from an economic perspective. And we showed, for example, that something like Justice 40 here in the US does not do very well when it comes to achieving those two goals at the same time. But there are other funding rules that can achieve that goal. And in the next phase, we are assessing how using different flood hazard data, for example, from the event-based approach and the response-based approach, can lead to different decisions when it comes to climate adaptation. We also work with colleagues at Rutgers, where they are developing building footprints for our study areas and also determining the first floor elevation. So they can then use our flood hazard information, combine it with tailored depth damage functions that actually account for how high the water level has to get before it enters the building to then conduct some impact assessment. We will also ingest synthetic data. Ning Lin's group at Princeton and Tony Broccoli's group at Rutgers, they're working on tropical cyclone in Princeton and extratropical cyclone at Rutgers. For the tropical cyclones, as I mentioned early on, we have relatively few in our observational records, so we can bolster our distribution and improve the framework by ingesting synthetic events. And the framework is flexible. It can ingest model hindcast data, reanalysis data, synthetic data for present day, and also for the future. So we will also assess how increasing sea level, something that Sönke Dangendorf's group at Tulane is working on, changes in storminess, changes in rainfall climate, lead to emerging hotspots of compound flooding, and how flood risk could change moving forward under those conditions. And last but not least, we are working with Franco Montalto and his team at Drexel. They have been running stormwater models, like sewer models, pipe flow models for years now in that area. And we are using some of those boundary conditions that we generated for our surface flood model to include into their pipe flow model activities to assess stormwater infrastructure performance, and going forward, hopefully also assessing different adaptation options to improve that. And I will stop here. Thank you very much for your attention. And again, if you have any questions now, or if you're watching a recording and have any questions later, please feel free to email me at this email address here at the bottom. Thank you very much.
Thank you, Thomas. Thank you very much. Nice presentation. That was very interesting. Very interesting. So is there any question for Thomas?
I have a question. Yeah, so as I was listening to this, I teach in a civil engineering department, right? And for our basic like engineering stuff, we basically say, yeah, rainfall, 100-year rainfall equals 100-year flooding. Obviously, from your perspective and all the great work you've done, you've shown that that's not the case, right? And my thought is just from this very simplistic point of view, do you feel like there's any way to incorporate some of the stuff that you've done in sort of basic engineering to try to help students in a simple way understand and do this stuff? Because you've got this really great complex modeling and copulas, and undergrads struggle with just basic statistics. So right.
Yeah, I hear you. I mean, I teach hydrology. I just finished my class, and again, I taught them the same thing, right? I said, this is what we do. I talk a little bit about the research and saying that we are moving in a direction where hopefully this won't be assumed to be true anymore at some point.
Mm-hmm.
But you're right. It's hard. I mean, even dealing with the univariate distribution and fitting a GB is for them, right?
Yep.
I do some of the more advanced stuff in the graduate class, but that's more coastal focused.
Mm-hmm.
We are working with a group to develop a manual of practice from ASCE that is currently under review, that should serve as a guideline for practicing engineers to start ingesting some of those more complex models into project design and risk assessment. That being said, I mean, of course, yeah, even for practicing engineers, they learn that back in school, right? So even for them, have been in the business for 10, 15 years, there are more and more now that are reaching out to us that are really trying to incorporate more complex approaches. And we are trying also to develop tools. So we developed an R package, R Shiny, where people can just upload your time series and then click through the different steps. It's still somewhat of a black box, obviously, if you don't understand what's happening behind the scenes, but at least it gets them to start using some of those methods. I just saw the latest version of this manual of practice, and I think it needs more work because it's still very theoretical. And I fear that if it's not boiled down more, it won't have the effect that we desire of people actually picking up those methods. But it's a challenge, right? We have statisticians in the group working on that part, and they write a certain way. And even though they collaborate a lot with engineers, and some of them are engineers by training, there's still a little bit of a gap between what they think is they just describe everything in a very simple way versus what a practicing engineer feels is an understandable way of explaining those things.
That makes sense. Yeah, it's good to hear that you're thinking about this and working towards some of this, even though it may be, years away from actually being practiced. I think it's awesome that you're working on that.
The water management districts, for example, here in Florida, at least, I know they have really started incorporating that. South Florida Water Management District, for example. And of course, yeah, the graduate students are being trained on this. So if they enter the workforce, they just hired one of my students. So they have now in-house expertise to keep doing those things. So slowly but steadily, I think we are moving in the right direction.
Yeah. Yep. That's awesome. Thanks.
Yeah, nice. Very nice. Any question for Thomas from audience? So I have a quick question, Thomas. So for calculating the lag time between the rainfall, the water level, so how much was in your case, the lag time?
That is a question for Praveen. I don't know the full range of lag times. I know it was a pretty wide range. I mean, sometimes it's a day or close to a day, and then it really becomes not really a compound event anymore. But still, flooding can happen, right? But it's just not compounding each other. What we did is we picked a rainfall event and we picked a non-tidal residual event, and they can come from different events. We made sure that it's okay to do that. We did a lot of testing if we can mix and match, and it turns out based on all the characteristics that we care about, we can mix and match. But then we took one of the time lags, either from the rainfall events that we sampled or from the storm surge events that we sampled. So at least that would be fully consistent based on the historically observed data. And some of them were almost on top of each other, right? Peak on peak. And then some of them were farther away. I don't know exactly how far and what the distribution of those lag times looked like.
I'm just curious to know whether there is any relationship between that time lag and the time of concentration of the catch.
Yes, I mean, that's, yeah. Avi Gori from Ning Lin's group has had a paper where she focused on that and showed that the lag time is really important from the flooding perspective. In our case, I think we found that the rainfall often precedes the storm surge, which makes sense, right? The storm often, especially the tropical storms coming from the ocean, the rain bands arrive, and then the storm surge propagates up the Delaware River. So there is this lag with the rain typically happening a couple of hours before. So I think that's what the distribution of those lag times looked like.
Great. Thank you, Thomas. Any other questions?
I will ask Sarah and Praveen to put that into the documents that you shared. If you can send me the email with that, if you want this to be included, I can ask them to add the information. You probably have a ton already in the US. But,
yes, the Google
Sarah
document.
has already done some work in Africa,
Nice.
and I think some work in Germany as well. She may be able to add a few more examples to that list.
Yeah, nice. This is a Google Doc. I put it in the chat.
Okay.
So,
yeah, I have the link.
So that we can have your work in the report. That would be great. Very nice. So any other question for Thomas you guys may have? So one quick thing is about our website. You can go through this website and see who is our next speaker, keynote speakers. We will not have a meeting in July because we would be at GHP, a meeting in Canada, and we will not have a keynote or meeting for July, but we will have, we started from August onward, and you can see the list of keynote speaker on our website. We will also share the recording. Thank you to GEWEX to helping us with the YouTube upload of the recordings. We'll send this recording to you guys in case if you're interested to share or to look at the presentation again. So again, since we don't have Dr. Juan today to provide some update on the his side of flood modeling, then I wish you all a happy weekend. And I want to thank you, Professor Wahl, for accepting our invitation and providing us with that nice type of flood presentation. Thank you, guys. Thank you. Thank you, Thomas.
Thanks.
Have a great weekend. Thank you.
You too. Bye.
Thank you. Bye.